Hi. Today we'll be looking at counting and probability, and one of the subtopics we're going to focus on is the rule of product. What is the rule of product? It's really simple. Let's say when a task consists of k separate steps, and the first step can be done in n1 ways, the second step can be done in n2 ways, the third step can be done in n3 ways, and so on. So all the way to the kth step, which can be done in nk ways, the total number of possible results for completing this task is given by the product of these numbers. So it's n1 times n2 times n3 times all the way times till nk. So let's say capital N, is the total number of possible results for completing the task. So let's look at a question from UKMT 2005, question 16. A hockey team consists of 1 goalkeeper, 4 defenders, 4 midfielders, and 2 forwards. There are 4 substitutes: 1 goalkeeper, 1 defender, 1 midfielder, and 1 forward. So let me just write it down. We have 1, 3, 4 defenders, 4 midfielders, and 2 forwards. And for the subs, we have 1 for each. So one midfielder, 1 forward. Okay, so the question says, given that a maximum of 4 substitutes may be used and there are still 11 players on the pitch at the end, how many different teams could finish the game? So what the question means by a maximum of 3 substitutes is that you have to choose 3 from those 4 subs. Okay, so now let's ignore what the question says about a maximum of 3 substitutes. Let's determine what's the total amount of teams that you could assemble if up to 4 substitutes are allowed. So if up to 4 subs are allowed. So this means you could have no sub, 1 sub, 2 sub, 3 sub, or 4 subs. And so how many goalkeepers do we have in total? We have 2, right? For defenders, we have 5. For midfielders, we have 5. And for forwards, we have 3. So what we're trying to do is, well, we have 15 players in total, and we could just try to assemble a team with, we don't really care how many substitutes we're allowed to take. So by doing this, we have 2 goalkeepers, 2 possible choices for goalkeepers, 5 possible choices for defenders, 5 possible choices for midfielders, and 3 possible choices for forwards. And that gives us a total of 150 teams in total. So there are 150 teams that we could put together, like 150 different teams that we could put together if up to 4 subs are allowed. Now, since the question says a maximum of 3 subs may be used, so let's consider this. So what we don't want from the total number is we don't want when the 4 subs are all used, right? So how many possible chances there are, how many possible teams there are when the 4 subs are all used? So again, so this is the scenario where all 4 subs are used, right? So we could substitute, we could have 1 possible choice for the goalkeeper because there's only 1 goalkeeper and 1 sub. So that's 1 times, we can have 4 different choices for defenders because let's say we have defenders A, B, C, D, right? So if we have defenders A, B, C, D and each of them, we could make it a substitute. we can put the substitute in its place. So we have 4 choices for defenders. And then the same idea, if you have, let's say, midfielders E, F, G, H, and well, essentially you have 4 choices for that. So we have 4 choices that a substitute can switch into. And for forwards, we have 2 choices. Right? So this is a scenario where all 4 subs are used, and which give us 32 possible teams. And since this is the scenario where we don't want, and the first 150 teams is the scenario, 150 teams is a scenario that is the total number of teams, we could use 150 to minus 32 to get what we want. So which is what we want is a maximum of 3 substitutes. So 150 minus 32, which gave us 118. And that gave us the answer of this question, B. Let's look at a question from UKMT 2006, question 13. The diagram on the right shows 5 disks connected by 5 line segments. So disk A, B, C, D, and E. 3 colors are available to color these disks. In how many different ways is it possible to color all 5 disks if disks which are connected by a line segment are to have a different color? Alright, so we know we have 3 colors to color all the 5 disks, and you might be wondering, well, which disk do I start from? Usually in this type of questions, I will start from the most unique disk, and in this case, since disk A, B, and C all connected to 2 other disks, only E is connected to 1 disk, to D. So I will start from disk E. So let's determine how many colors we can color disk E first. 3, right? Because it's the first we determine and it has all the choices. So if we want to color E, we have 3 ways. Now, the only disk that's connected to E is D. Therefore, D's color is affected by E's color. So how many ways can we color D? 2 ways, because we want disks that are connected by a line segment to have different color, right? So for every color E has, we want D to have the other 2 possible colors to color it. So how many ways can we color E and D in total? So it's simple rule of multiplication. We just times 3 and 2 give us 6 ways. Now, let's move on from disk E and D to B and C, because B or C are the only disks connected to disk D other than E. So there are 2 cases that we can color B and C in this scenario, as you can say. The first case being case 1 being B and C has the same color. B and C have the same color. And the second case, you might have guessed already, is B and C have different color. I'm separating this because we know that B and C are not connected by a line, right? So they can be the same color. And they can also be different colors. So I'm just listing out as 2 cases so it's clearer to know what we're doing and so that we don't have any repeats. And repeats is what we don't want in these counting and probability questions. Okay, so let's look at case 1 where B and C has the same color. So right now, we know E and D, the color of E and D is determined. So how many ways can we color B and C? 2, right? There are both 2 ways to color B and C. Well, because it can't be 3 because it can't be the same color with D. And so it has 2 remaining colors to color B and C for every color D has. And now, since B and C is determined, how many ways can we color disk A? also 2, right? Since B and C is the same color, and disk A can't be the same with B and C, it has 2 remaining ways to color itself, so 2. And so for case 1, we have 2 times 2 equals to 4, and if we times the 6 ways before for E and D, we have 6 times 4 is 24 ways in total for the first case. Now, for the second case, where B and C have different colors. Now, if these colors determined, and we have 2 colors left to color B and C, since B and C is equally important, you can choose to focus on B or choose to focus on C, whatever you want. But in this case, I'm gonna focus on C. So let's say D's color is determined, right? So how many ways can we color C? 2 ways. How many ways can we color B? Since we want B and C to be different, we only have 1 more way to color B. And how about A? Well, this is a bit awkward for A because B and C, they used the 2 colors and there's only 1 remaining color left to color A so that they don't have the same color, right? So this is 2 ways. Now, as I said earlier, you could focus on C or you could choose to focus on B. Let's see if you choose to focus on B now. So if the color of D is determined, how many ways can we color the color of B? 2, right? So there are 2 ways to color the color of B. And since we don't want B and C to be the same, there's only 1 other way to color the color of C, because C is also connected to D. There's only 1 way, and also there's only 1 way to color the color of A, or the same way the other way around. So in case 2, where B and C has to have different colors, we have 2 ways to color them with A. And if we time the 6 before, we have 2 times 6 is 12 ways in total. The 6 is just adding on the possible chance to color E and D. So for every color of D, we have 2 ways to color A, B, C if they're different, so on. So we have 24 ways in total for case A and 12 ways in total for case 2. Now, if you just add up these 2 numbers together, well, we get 24 plus 12 equals to 36 ways. Hence, this is the answer for question D, 36.